All right, these are going to be the solutions to our angular momentum worksheet. So, first one, how is angular momentum defined for a rotating object? This is going to be any object that has a fixed pivot point. And it's spinning in some way. So, for that, angular momentum is I times omega. If we remember linear momentum, linear momentum is mass times velocity. So when we look at its rotational equivalent, we're using L for angular momentum. Instead of mass, we're going to use the rotational equivalent of mass, rotational inertia. And instead of V, we're going to use the rotational equivalent of velocity, which is angular velocity. Now, when we do units for that, the units for rotational inertia, I, are kilogram meters squared, and the units for omega are radians per second. Radians are just a placeholder, so this is kilogram meters squared per second. How is angular momentum defined for an object which is not rotating? So this is a point particle moving in a straight line. Okay, so for that, L is going to be equal to mva. And A is the kind of tricky part here. A is the straight line distance between our line of action and whatever the reference point or the pivot point for the system is. So it's going to be really important every time we're dealing with an object moving in a straight line and we're concerned about its angular momentum to figure out what that A is going to be. The larger our line of action is, the further our line of action is away from that point of rotation, the more angular momentum we have. How is the angular momentum of a point particle a relative measurement? This is because of the A. It must be taken with respect to a reference point or a pivot point. Think about it if you're throwing a ball at a board that's standing up. If you throw it towards the bottom, it's not going to cause it to rotate a lot. If you throw it toward the top, it's going to rotate a whole lot because you're increasing your A. So it must be taken around a specific pivot point because where that specific pivot point is changes A, changes the value of our angular momentum. How is angular momentum changed? This is what torques do. Outside torques to the system changes our angular momentum. The other way of saying that is that L is constant when the system or the objects in the system are free to spin. And this whole free to spin thing is just another way of saying that the net outside torques are equal to 0. So when a figure skater pulls her arms in close to her body, first off, she's free to spin. What that means is that before she pulls her arms in and after she pulls her arms in, she's going to have the same angular momentum. That's the first thing. As she pulls her arms in, that decreases her moment of inertia. Moment of inertia, her rotational inertia is something like mr squared. By pulling her arms in, that r gets smaller. So if I decreases, omega has to increase to make up for that. Same thing with the diver. In the air, the diver is free to spin, so L is conserved. by changing his rotational inertia, his omega will change as well. Pulling in arms and legs would make I go down, omega would go up. Going in the opposite direction and throwing out his arms and legs would make his I increase and his rate of spin decrease. So, the student stands on a small, frictionless platform that is free to rotate. He holds a bicycle in his hands, oriented so that the axle of the wheel is vertical and the wheel itself is horizontal. He pushes the wheel clockwise, causing it to rotate. So, since he's on this spinning platform, and it says it, the whole system is free to rotate. That's free to spin. That means net torque is 0. L initial is equal to L final. That's great. So at the beginning, L initial is equal to 0. So at the end, L final is going to be L of the wheel plus L of the student platform system, right? So the rotational inertia of the wheel is going to be going clockwise. The rotational inertia of the student, the rotational momentum of the student has to be going in the opposite direction, counterclockwise, in order for those things to cancel out and equal 0. They must be opposite in direction in order for that to cancel out. And you saw this when you sit on the platform and spin the wheel. You spin the wheel one way, you will spin another way. You have equal and opposite torques acting on you. All right, so we have a platform that has this mass, this radius. It's a small cylinder, so 1/2 mr squared. The platform rotates at 10 radians per second counterclockwise. So this is a platform. It's an object spinning about an axis. We're going to use I omega. So L is going to be equal to I, which is 1/2 the mass, 40, times the radius, 2 squared, times omega, 10 radians per second. So that comes out to be 800 kilogram meters squared per second. That's the angular momentum of the platform before anything happens. So now we have this platform moving, and we're going to exert a force of 30 newtons to the right, perpendicular at a point 1 meter below what's going on. What happens to the angular momentum? So we're going to explain it and we're going to calculate it. So let's calculate it first. Torque is equal to the change in angular momentum over the change in time. The way this works, net torque is equal to I alpha. That's Newton's second law for rotation. So net torque is I times the change in omega over the change in time. Well, that's the same thing as saying the change in angular momentum over the change in, not L, over the change in time. This right here, I times change in omega, is the same thing as delta L. So what we need to look at is our torque. So we have 30 newtons 1 meter below. The torque from that force is 30 newton meters. It's the force times the radius, and those things are perpendicular. So what's going to happen is that the angular momentum is going to change, right? Now if we go back and look at this, this thing's already spinning at 10 radians per second clockwise. This torque is going to act to increase the angular momentum of the system. So if we rearrange this, the change in angular momentum, delta L, is going to be the change in time times our torque. So delta L in this case is going to be the change in time, 4 seconds, times our torque of 30 newton meters. Our change in angular momentum is going to be 120 newton meter seconds. And it's going to be an increase in angular momentum. So to explain that, the force is going to cause the wheel to speed up in the counterclockwise direction because it is a counterclockwise torque. An increase in angular speed is also an increase in angular momentum. So the angular momentum is going to increase. Another way to say that is to say a net torque must change the angular momentum. We're applying a net torque, so the angular momentum must change. How could the force be modified to create a greater change in angular momentum? So what we have here is delta L is equal to time times our torque. So delta L is equal to time times force times radius. So we could increase the force, or we could increase how far the force is from our pivot. All right, we have a bar. The bar is already spinning, and we're going to push down on it with this force, and I want the magnitude of the force. Before we go on, this is my pivot. That should be ml squared. So the moment of inertia of this thing is the mass, 8 kilograms times the length, 0.5 meters long, and we're going to square it. So the rotational inertia of this thing comes out to be 2 kilogram meters squared. Omega 0 is 4 radians per second. Omega final is 12 radians per second. And the time that the force is in contact with the bar is 0.2 seconds. So the thing that puts everything together is net torque is equal to change in angular momentum over the change in time. What we need is a torque. Well, if that's 0.25 meters, the torque from this force is 0.25 F. So 0.25 F is equal to 2 times the change in angular speed, 12 minus 4, divided by 0.2. We can rearrange all of those things, and when we do so, we find F to be 320 newtons. So we're using this idea of net torque is change in angular momentum over time to find out how big that force was. Okay, that was all just for single rotating objects. What we're going to move into for the next few problems is conservation of angular momentum when objects run into each other. And what that's going to involve is objects moving in a straight line. So we're going to have to remember that for an object moving in a straight line, the angular momentum is mv times a, where a is the distance from the line of action of the moving object to the pivot, to the reference point. So in this question, what's going to happen is we're changing our reference point for the same object, picking a lot of different reference points and seeing what's going on with my object. Now, it does not matter how far away the object is from each reference point. Because the object is moving, all of those distances are going to change. We don't care about that. What we care about is the line of action of our object. And that line of action is a straight line extending forward and backward through the object parallel to the velocity. So, all that matters is the distance between the line of action and our point. So A is 2 meters away from the line of action, B is 2 meters away from the line of action, C is 3 meters away from the line of action, D, that's 30 degrees, D is that far away from my line of action. That's 2 sine 30, that's 1 meter away, and E is right on the line of action. So, we want to rank these guys. What we need, the mass and the velocity are going to be the same for each point. All that matters is the A. The bigger A gets, the bigger the distance from the line of action to the pivot, the bigger the L gets. So the largest one, the angular momentum about point C, is the biggest one. Everything else is smaller than that. Next you have A and B. They're equal to each other, so LA equals LB, and those are bigger than the angular momentum for D, which is bigger than the angular momentum about point E, because that's 0. The line of action passes through that point. There's no changing angle. There's no angular speed associated with that point. So let's take that and use it. We're going to take an arrow, 2 kilograms moving at 20 meters per second. We're going to fire it at a wheel, and it's going to hit that wheel on its edge. So, we're using here, because we are free to spin, what we're using is the idea that the initial angular speed is equal to the final angular speed. The initial angular speed is mva. So because this is the only thing moving. This is not moving to begin with, so it doesn't have any initial angular velocity. So it's going to be 2 kilograms times 20 meters per second times 0.8 meters. So the initial angular velocity of this system, because my line of action is here, and so this is the distance between my line of action and the pivot for the system, 0.8 meters, the initial angular speed comes out to be 32 kilogram meters squared per second. Now, that's the initial angular speed. That's the initial angular momentum. The final angular momentum is the total rotational inertia of this system times the rotational speed of this system. So the final angular momentum, since these are two objects stuck together, is the rotational inertia of the wheel plus the rotational inertia of the arrow times the final angular speed. When they give us the rotational inertia of the wheel, it's the arrow that's a problem. So the arrow sticks into this thing and it's going to rotate. So what we have for the arrow is a single mass rotating about a point. Anytime we have a single mass rotating about a point, the rotational inertia is m times however far it is from that point, the radius squared. So, in this case, L final is going to be the 80 kilogram meters squared, sorry, that's misdone, 80 kilogram meters squared plus the mass of the arrow 2 times the radius of the arrow 0.8 squared times that final angular speed. So my expression for the final angular momentum is, I think, 81.2 kilogram meters squared times omega. So in order to find out the final angular speed of this system, I'm going to say L initial is equal to L final. So that's 32 kilogram meters squared per second is equal to 81.2 kilogram meters squared times omega. When we do that, omega comes out to be really close to 0.4 radians per second. Does the linear momentum of the system change as a result of the collision? No. Oh, sorry. It says linear momentum. Yes, yes it does. The linear momentum goes from this thing moving, initial linear momentum is just mv, to the thing spinning around. Well, there's no really any linear momentum associated with that, so you bet it changes. The pivot or the axle of the wheel acts as the outside force on the system. Anytime we have an outside force acting on a system, linear momentum is not going to be conserved. How would the answer to A be different if the path of the arrow were to be shifted downward, such that the arrow struck the point P instead? So what we're going to do is come down here. Well, that's not quite it. We're going to fire our arrow, and we're going to land at that point. My radius is still 0.8 meters. So, the A has become smaller. The line of action is closer to the pivot for my system. If that's the case, the initial angular momentum is smaller, and so the final angular momentum is smaller. That means we're not going to rotate as fast, and we're going to go in the opposite direction. All right, 12. We got a platform that can rotate without friction. Good for it. So for this whole thing, because it can all rotate without friction, we are free to spin. So the first thing we're going to do is calculate the angular momentum of the buoy platform system. This is a spinning system. The buoy is standing on the edge, so we'll draw that again. So the buoy is standing out here on the edge of the spinning system. It's going to be the rotational inertia of the buoy plus the rotational inertia of the platform times the angular speed of the platform. Those two things are together, moving together, so we're going to allow them, their momentums go together. So L is equal to the buoy, that's a point mass, so it's mass of the buoy times the radius squared, plus the rotational inertia of the platform, 1/2 mass of the platform times the radius squared times the speed. So now we can plug all those numbers in. The mass of the buoy is 40 times 2 squared plus 1/2 the mass of the platform. Oh, sorry. Mass of the buoy is 60. Plus the mass of the, plus 1/2 times the mass of the platform, 40, times the platform's radius, 2 squared, times omega, which is 10. Put all that in there, and we get 3,200 kilogram meters squared per second. That is the initial angular momentum of our system. The buoy slowly walks to the center of the platform until he's straddling the axis. Boom. And he's not going to have any angular momentum because he's essentially standing still, spinning around. What happens to the angular momentum of the system? What happens to the angular velocity of the platform? So for the system, L initial is equal to L final because we have no outside torques. We are free to spin. However, because the boy is losing angular momentum, the platform is going to have to gain angular momentum, right? The system stays the same, but the boy loses L, so the platform gains L, meaning it speeds up. So, if we're going to solve for that, the initial angular momentum is equal to the final angular momentum. Well, the initial angular momentum is 3,200, and then the final angular momentum, as the boy walks in, his radius shrinks. So what that's going to do is make his rotational inertia 0. The platform's rotational inertia doesn't change. It's still 80 times omega final. What that's going to do, just 3,200 divided by 80, that's going to give me 40 radians per second as the final angular momentum. As the final angular speed. We see that it increases from 10. Because the boy, as he came in, lost angular momentum, the platform gained it. Platform is brought to rest. The boy is returned to the edge. He then runs along the perimeter platform with a constant linear speed of 6. Calculate the angular velocity of the platform and indicate its direction when the boy is running and when the boy stops running. So, if it's brought to rest, the initial angular momentum of the platform boy system is 0. When he starts running, the platform begins to move. And after he stops running, the platform is going to be stopped. So omega of the platform after the boy stops running is 0. It's a little bit more complicated as the boy is running. So the initial angular momentum is equal to the final angular momentum. So 0 is going to be the angular momentum of the boy plus the angular momentum of the disk. Well, the platform, sorry, we'll say platform. That's going to tell me that the angular momentum of the boy is equal to the negative angular momentum of the platform. The boy's angular momentum is his rotational inertia, which is the mass of the boy, 60, times his radius, 2 squared, times omega. The omega for the boy is 6 over 2. That's the speed. Omega is equal to V over R. And that's going to equal negative rotational inertia for the platform, 80, times omega for the platform. So the omega for the platform comes out to be negative 9 radians per second. That negative sign just means that the platform spins counterclockwise. 13. An experimental cannon is constructed out of a solid sphere with a muzzle on the top, which launches the cannonball perpendicular to the sphere's radius. The sphere is going to rotate around its center. So, that means it can spin freely. Because it can spin freely, the momentum is going to be conserved. Initial angular momentum is equal to final angular momentum. So, the initial angular momentum is 0 because everything is at rest. The final angular momentum is the angular momentum of the ball plus the angular momentum of the gun, or the cannon. I guess we'll call it a cannon. So, so that tells me that the angular momentum of the ball is equal to the negative angular momentum of the cannon. So the ball is a straight object moving in a straight line. It's mv times a, and the cannon is going to be the rotational inertia of the cannon times its rotational speed. So for the ball, mass of the ball times the velocity of the ball. The a in this case is the distance between the line of action and the radius. The line of action and the edge of the cannon. That's just the radius. And that's equal to negative I omega. It gives all those numbers. So we want the velocity of the cannonball after launch. So the cannonball has a mass of 2 kilograms. We don't know its velocity. We do know its radius, 1.5 meters. And the cannon has a rotational inertia of 100 kilogram meters squared. And it's moving with a rotational velocity of 2 radians per second. Now, that's going to be in the counterclockwise direction. We have a direction that goes along with that. So, that means everything over here is going to be in the clockwise direction. That's what that whole negative sign is for. So if we can eliminate this because we know that the ball is going to be going this way and the cannon is going to be spinning that way. So our velocity comes out to 200 divided by 3. The velocity of the ball comes out to be 66.7 just meters per second. Again, still using the idea that the initial angular speed is equal to the final angular speed. Sorry, the initial angular momentum is equal to the final angular momentum.